everyone. We are going to focus on section 3 of chapter 18 on acids and bases. This has to do with differentiating between strong acids and weak acids, or strong bases and weak bases. We're also going to talk about how strength of an acid is related to how they dissociate. Another thing we're going to talk about is a concept called Ka as well as Kb. Ka that you can see here in this objective is called the acid dissociation constant. So it's really trying to figure out the concentration of an acid based on how much that acid is going to dissociate. And we are only going to use that with weak acids, which we'll see in just a second. Kb is very similar to Ka, and Kb is the base dissociation constant. And with Kb, it's going to be, like we said, very similar to Ka. And let's just kind of start talking about these so we can get there. So in terms of strength for acids and bases, we classify an acid or a base as being strong according to how much they ionize when they're in water. So if an acid is a strong acid, then that means it is going to completely ionize when it is in an aqueous solution, when it's in water. So this means that it's going to ionize 100%. So there are 6 strong acids and there are 8 strong bases that you are going to have to memorize. And those 6 strong acids and those 8 strong bases will always ionize completely. So what exactly does that mean? Now, I wrote your list up here that you'll need to know. These are your 6 strong acids. Your 6 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, perchloric acid, and then nitric acid. So those are your 6 acids. Those are the strong acids. And then everything else we kind of just consider to be weak. And then these are your 8 strong bases. So the 8 strong bases that you have right now are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. All of these come from the alkali metal group. So if you can remember that I have 5 of them that come from the alkali metal group, the other 3 come from the alkaline earth metal group. So I have calcium hydroxide, barium hydroxide, and strontium hydroxide. And all of these 8 strong bases have another big thing in common, and that is that they all end in hydroxide. So my 8 strong bases have hydroxide, and then 5 of them come from the alkali metals, 3 of them come from the alkaline earth metals, so if that helps a little bit. In terms of strong acids or strong bases, what makes an acid strong is that it completely dissociates into its ions once it's in water. So if I have HCl and I add that to water, I am going to get hydrogen ions and chloride ions. I'm not going to get any extra HCl as a product. It completely breaks apart to its ions. If I look at HNO3, that's another strong acid, it will do the exact same thing. It's going to break apart into hydrogen ions and then nitrate ions, and I'm not going to have any extra HNO3 on that product side. A strong base is the exact same way. So lithium hydroxide, when it dissociates in water, it's going to break apart into lithium ions and hydroxide ions. So I don't have any of that lithium hydroxide on the product side. It's just completely breaking down. Okay, in terms of a weak acid or a weak base, weak acids and bases only ionize a little bit or slightly when they're in water or in an aqueous solution. So strong is where they're completely ionizing, and weak is where I only have a few ions that are created, and I'm still going to have some of that original reactant left. Now, one thing that I want to make sure that we understand is that strength is very different from concentration, because strength is dependent on how many ions are present, meaning like how many ions am I creating whenever these compounds are dissociating. But concentration depends on moles. How many moles do I have? And we're going to talk a little bit more about that. But I just really want to point that out. Strength, very different from concentration. Okay, so again, strong means that it forms many ions. It has 100% ionization, meaning that it will dissociate completely into ions. MgOH2 is magnesium hydroxide. Actually, guys, that should say calcium hydroxide. So let's pretend like this does not say Mg. Let's pretend like it actually says Ca. So calcium hydroxide is a strong base, falls completely apart, so nearly or almost, if not all, 100% of it will dissociate into ions when it dissolves. Let's go to this. So this would be a strong acid dissociation. I started off with an acid that, just a generic acid that we're going to call HA. And when I include that or react that with water, it's going to break apart into my hydronium ions, which is just hydrogen ions. And then I'm going to have this A- left. So I started off with this acid, and it completely broke down to hydrogen ions and then the A- ions. I can call this hydrogen ion because this is still just attached to water. So it's hydronium, but ultimately here I'm making my hydrogen ion here. It's just in water. So this is breaking down completely. One really big hint is that notice that this is not a double arrow. It's not reversible. This is a complete breakdown. I can't go back over here to the reactants. So this is going to break apart into the ions completely. So this gives me 100% ions. This is different from a weak acid dissociation because it only partially ionizes. So again, I started off here the same thing. Let's say that I have some generic weak acid, and then I add that to water, and I don't get as many hydrogen ions and then the A- ions. I only get a few of those. So if I only get a few ions, I'm just left with the product of what I started with here. So I may have gotten a few ions, but then I still have a whole bunch of this original acid remaining. So that means that I have a very weak acid. There's a very little dissociation going on. And in this one, I can see that I have this reversible arrow here. I have my reversible arrow because I need some more acid to try to get some more ions to dissociate. That's what could make it get a little bit stronger. So in a weak acid dissociation, I'm going to see this reversible arrow, but in a strong acid dissociation, it's going to completely ionize. So I only have that arrow going towards the products. Now, when we are measuring strength, specifically, we want to look at measuring strength for a weak acid. We will use something called Ka. We know that a strong acid will dissociate completely into ions. What we don't know is we know a strong acid will dissociate completely into ions. But what we don't know is how many ions could dissociate in a weak acid. Really, how weak is the acid that I'm working with. So let's say that we have this again. I add my acid, just a general random acid, HA, with water. And it will dissociate into these two ions. But it's a weak acid because I see here that I have this reversible arrow. So when I say here on this second bullet point that it makes an equilibrium, this means because I can't produce as many of these ions as I want, the reaction is going to move back towards where this acid is reacting with the water, so it will try to dissociate into more ions. The goal is to get more ions because then that means the acid can be stronger. So we have created something called Ka, which is called the acid dissociation constant. And Ka is how we can figure out exactly the measure of the strength of a weak acid. And that's going to be dependent on the products that are made and then that reactant that's in the water. So how I write Ka? Ka is going to be equal to your products over what your reactants are. Now my products are hydrogen ion, and then I had my A minus ion, and then my reactant was HA. Well, why didn't I have to use water in this? Because technically it's all happening in water. Well, even on the product side I have water, and on the reactant side, even though we don't write it, I still have these ions in water. And I have this acid in water. So if I added water up here and water down here, what would happen to those? They would cancel out. So that's the reason why we don't add the water in there, because they're going to balance each other out anyway. It's present on the reactant side. It's also technically present on the product side as well. So if I want to find the acid dissociation constant, I am going to write the concentrations of my products, which were H plus and A minus in this case, over the concentration of my reactant, or my original acid, which in my case here was HA. The larger the Ka value, the bigger value Ka is, the stronger we consider the acid. That means that I have more products as ions. I have less of this original acid, and I have more ions present if Ka is going to be larger. So that means that I'd have a stronger acid. So let's look, for example, we can also look at a base, because Kb will be exactly the same thing as Ka. Our base dissociation constant is called Kb. Let's say, for example, I have a metal hydroxide plus water is going to make some metal ions and some hydroxide ions. So we know that strong bases dissociate completely, but I know that weak bases don't. And I know that this is a weak reaction because I see this double arrow here, this reversible arrow. So I need to find then the base dissociation. I need to find Kb to figure out how strong this base actually is. So just like what we did with Ka, we're going to do the exact same thing for Kb. So Kb is just taking the concentrations of my products, so that's my metal, that's my hydroxide ion, and then that's going to be over my original base. And again, I'm not including water in here because that water is present on the reactant side, but it's technically present over here on my product side. So again, if I had water up here and water down here, it's the same thing, so they're really canceling each other out. That's why I don't have to include the water. Now, let's do, I think we have some examples here. Also, this will be a stronger base if Kb is larger. It means I'm producing more ions. So the more ions, the more ionization that's happening, the stronger the base. And that's why we get our strong acids and strong bases, because they completely ionize. Okay, I have on here C handout, but let's do an example. Let's say that we have hydrofluoric acid, and we're going to add that to water. I'm going to get hydrogen ions and fluoride ions. This is not one of my 6 strong acids, so because it's not one of my 6 strong acids, I know that this has to be a weak acid. I also know, as a hint, this has a reversible arrow here, so that also indicates that it's a weak acid. And for a weak acid, I'm going to have to write that Ka, that acid dissociation constant. So Ka, like we said, is going to be equal to the concentrations of the product over the concentrations of the reactants. So I'm going to look at my products here. I made hydrogen ion and I'm making fluoride ion. So I'm going to write, because remember my brackets mean concentration. So I have my hydrogen ion times the fluoride ion over my reactant, which would be HF, over the concentration of hydrofluoric acid. This is my Ka dissociation. This is my acid dissociation constant. So I can give you numbers to plug in here that we can actually calculate Ka, But right now, I am just happy that we can write this. This is kind of just where we're going to stop right now. And AP will calculate them. But right now, I just want you to write this. So we are going to finish talking about strength in the next video. And then we'll also talk about buffers and titration as well in the next video. So I hope you guys have a great night, and I will see you on Monday. Bye.